What I want to look at here is, and hopefully I can do my drawings well enough, is supersonic shockwaves. An interesting thing. So we'll use a plane because it's planes that can travel faster than that. And what we're going to get, if this is a plane and it's traveling at the speed of sound, so we see this is like an extreme Doppler, so your Doppler diagrams will have helped us, then we're going to get a series of circles that are all going to meet at this point, because the plane is always keeping up with the waves it has originally produced. So there's no waves in front of it because it's always travelled at that speed. So it's like on the edge. So we go to this biggest wave here, then it was produced when the plane was there. The plane's kept up with the front part of the wave, and the back part of the wave's gone off in that direction. So we get this interesting diagram like this. Now that's not the one that's the most interesting. The most interesting one is where the plane actually goes faster than the speed of sound. And so we would still have this big circle, but instead of the plane being at the front, it's got a head. So the plane's here now. So over here, what we're going to have here is a whole series of circles, and the angle at which they form, if we were to draw this angle here, totally depends on the speed of the plane. And we can figure this out reasonably easily. We can go back to a certain point, if you like, and look at the time it's taken the plane. So if we go back to, let's just try and make it a right angle. So from here, that's a right angle there. If we look at this one here, and we're looking at this angle here, then we can say sine of theta is equal to, well, what is it equal to? It's equal to Vt, okay, over Vst. Okay, so if we're looking at that, we've got the sine, which is the Vt is here, this top here. That's how long it took the wave to cover that distance. But in that same time, the plane covered this distance. So the sine is Vt opposite over the hypotenuse. So that's going to give us an angle. And you can see that that angle totally is going to be dependent on how much faster the actual, because we can cancel the t's, they're over the same time, how much faster the plane is going than the wave, because this top one is Vw over Vs. So you can see that when they're equal, that would be 1. That's the situation we've got here, and the sine of 1 is 90 degrees. So as the plane gets faster and faster than the actual speed of sound, this angle gets smaller and smaller. Now, it's these leading edges which are what we call the shock wave, because they're the front of all the waves, the crests, and they're all on that line. So it's got this shock wave. So the angle that that shock wave forms behind the plane depends how much faster the plane is going than the speed of sound. But you can see that that shock wave is moving along with the plane, and that's what people hear. And you could certainly hear 2 of them often. Just thought that was of interest and worth doing.